Hi everyone, greetings from India, and the topic for today's discussion will be DC-DC converters. So, if you look the industries around you, maybe a manufacturing industries or an automotive industries or a solar industry, which is a part of renewable energy industries, so they have something in common, and what is that? They all work in some form or other DC voltages, and they face a problem regularly with them, that is they have higher DC voltage and they need to step it down to a lower DC voltage. For example, in four wheeler industries, if you see the 100-volt DC from the battery pack, they need to step it down up to 80-volt DC starting from 0.5 volt to power up their auxiliary loads. So there can be n number of auxiliary loads in the vehicle. For example, there can be a USB charging point, they have to light up the boot light or the LEDs. So as an engineering student, if from a college, if you participate in a competition and the topic is to design a DC-DC converter to step down voltage, so DC voltage maybe from 60 volt DC to 5 volt or 12 volt DC, what will be your approach? So here comes the idea of buck converter, which is a type of DC-DC converter. And before proceeding ahead with the video, I need you to have some prerequisite that will be easy so that it will be easy for you to understand the concepts explained later in the later part of the video. So the very first prerequisite will be a basic understanding of buck converter. The second will be the basic understanding of transistors. So if you are well versed with these two topics, proceed. Otherwise, drop a comment in the section below and we'll see if we can make a video on that too. So let us start with a very basic circuit diagram of buck converter. So we term at design 1. So this is our switch S, this is inductor L, capacitor C, there will be a freewheeling diode D connected, and this is our battery, this is a resistor R, and these all are connected to the ground. So let me label this. So this is our V input side, resistor R, diode D, resistor R. The output is taken across the load resistor RL and the capacitor, and so this is what we call as a basic non-isolated DC-DC buck converter, or simply the buck converter. So now if we see the V output, it's a function of V input and the duty cycle D of the diode D, freewheeling diode D. So in order to improve the efficiency of this whole circuit, we need to look at different component that can cause inefficiency. So the very first component is switch, which is the contributing factor to inefficiency 1, labeled as inefficiency 1, and the second is diode D. So let us do a very first design change. That is how the engineering part works. You make a basic circuit and then you continue to improve it. So we'll say a design change 1 and we'll look at the switch. So now let me draw a switch. So this is a very simple switch. It has two states, on and off, and we are going to replace it. So our requirement is, since the switching needs to happen at very high frequency to minimize the losses, so the requirement will be high frequency switching, and the switching should be in the order of kilohertz. So what is the best component that comes into mind with this requirement? There is nothing else other than the power MOSFET. So let me draw a quick symbolic representation of that. So this side is my drain, source and gate. So let me replace the switch in the ideal circuit to the MOSFET which we have just drawn. So this will be our voltage battery pack, this, and the source side will be connected to freewheeling diode, the inductor L, the capacitor C, and the resistor R, and this is the place where we take the voltage output, and this is V in. So now the resistor R voltage is taken across resistor R and capacitor C, which is connected in parallel. So in future we'll remove the resistor R. Let me label the other component, inductor, capacitor and diode, and let me label the MOSFET as well, drain, source and gate. So we have done our very first design change. Now let's take a look at the second component, which is our diode. So we are going ahead with the another change, design change 2. So now if we draw a diode, and in diode if we try to push the current through the diode, there will be a voltage drop V across it. The voltage drop V will be in the range of 0.7 to 0.8 volt depending upon the diode you have chosen. Now, and the conduction losses in the diode will be the current ID and the voltage of VD and the duty cycle 1 minus D. So in order to reduce the loss, what we're going to do is we going to replace this with a MOSFET as well, like we did in the switch. So let me redraw the circuit, basic circuit again, design change 1 to design change 2. So we'll introduce a switching MOSFET. This is our switching MOSFET marked in green. Now with the red I'll mark the diode D, which we have just replaced with another MOSFET. The drain of MOSFET 1 will be connected to battery. The source and drain of the second MOSFET will be connected. The inductor will be in the place, the capacitor C, and these all are grounded, and we are take output voltage across the capacitor. So let me label the MOSFET M1 and let me label the diode MOSFET as M2. So let me label the other part of the MOSFET, drain, source, and drain and source for the second MOSFET as well. So the first MOSFET is known as high side MOSFET and second MOSFET is known as the low side MOSFET. So what do we exactly mean by high side MOSFET and low side MOSFET? So here comes the idea of the transistor. So let us take a quick recap on the MOSFETs. So let me start by drawing a symbolic representation of the MOSFET. So this part is called gate, the drain, and the source. This is equivalent to a switching circuit where the top part is represented as drain, bottom is switch, and the left part is termed as gate. So if we connect the drain to the positive rail supply V in and the source is connected to ground via resistor R, so and we apply a PWM on and off signal at the gate, what will happen? So we need to look at the 2 point D and S, the voltages at the 2 points, specifically at drain and source. So in on condition, what will happen if the switch is closed? The drain and source, what will be the voltage drop across these 2 points when a current is flowing through it? So according to the formula, delta V is equal to I into R. Resistor R is equal to 0 as we consider ideal. So delta V is 0, which means VD and VS are the same potential. Then only delta V can be 0. So VD is equal to VS. Now drain is connected to the V in, so which is equal to V in now. So this is what high side MOSFET is. VD is equal to VS is equal to V in. So if you remember this circuit, it will be an easy thing to understand. Every time you shouldn't by heart it. So just remember the circuit and it will be easy to understand. So let me shrink down this part of the content so that I can draw a low side MOSFET as well. So for low side MOSFET, let me start with symbolic representation again. The drain, source, and gate, D, S, gate, and S. So now if the source is connected to the ground and the drain is connected to positive supply rail, again with the resistor R. So what will happen when we give an on-off supply, which is a PWM signal at the gate? And so we need to look at the on state. What will happen in on state? So again we need to look at the voltage at drain and voltage at source when a current I flows through it. So in on state, source is connected to ground, which means VD is equal to VS equal to 0 volt. So that is what we call as a low side MOSFET. So that is the only difference when a resistor R is connected to ground via source and when a resistor R is connected to positive supply to the drain via V in. So that is what the differentiation comes in, where the resistor is placed and drain is connected on the positive side or the drain is connected to the lower potential. So when we analyze the circuit, both high side and low side MOSFET, in on condition, what is the voltages on the drain? If it is connected to positive supply via directly or to a negative supply via resistor R. So if you remember the circuit as mentioned, the switch simplified circuit will be easy to understand. See you in next video.